Good morning, you all. Today we're going to do a little vector addition. Now, today we'll review much like a math class, and you'll see a little bit from what we did from our unit with projectiles, and then some additional things. And once we get into later tomorrow or into Friday, you'll see the point of doing all of this math stuff with how we deal with forces. So the very first thing you guys need to do is you got a packet from me today. So use your packet and just kind of follow along with your notes, and then at the end there's some ones to do on your own. So the very first thing you guys need to understand is you need a definition of what's called a resultant vector. Now you guys, we've looked at component vectors of the resultant, but we never called it the resultant. But your resultant vector is what's known as the sum of two or more vectors. And there's lots of ways that you can add vectors, so I'm going to show you some examples. Example number one. Let's say that somebody runs to the east at 7 meters per second. Plus, they decide to run the next part of their race at 10 meters per second. Well, you would say they have a resultant velocity. And if you look, since this is going east and this is going east, you can add the two vectors together and get what's called the resultant velocity. And that would be one long vector, and just simply add it together and you get 17 meters per second. You can show the vector and you could write that it goes 17 meters per second east, because vectors always have a magnitude, which just means size, and with a unit and a direction. So that was pretty easy. So now let's do example 2. Let's say that for some reason an elevator has an acceleration downwards because of its equipment of 5 meters per second squared. But the rope on it is making it accelerate upwards at 10 meters per second squared. Again, these are two vectors, so you can add them. Now, since they're going opposite directions, I'm guessing you can guess what we might do with them. And you would be correct in the fact that we are going to subtract them. Now, since they're going directly opposite, we can do that. Since they go same direction, we can add them. So we have 10 minus 5, which you all have known for a long time is 5. So we can show this again with a vector as the resultant vector being 5 meters per second squared. And I forgot to write my 5, so there's 5 meters per second squared. Or you could write 5 meters per second squared up or north, however you wanted to do that. And again, this would be your resultant. Okay, so it makes it nice when they're parallel or 180 degrees from each other. But there's also something else that we're going to do. And that is, what if they are perpendicular to each other? So let's say that somebody walks to the east 20 kilometers. And then they walk on a path and they go north 10 kilometers. How do you add something that is 90 degrees to something? Well, hopefully, like I said, this will relate a little bit. You start to see a triangle form. And so your resultant, if we redraw our triangle here, just to make it nice, 20 kilometers, 10 kilometers, you notice I add them head to tail, okay, is right in this direction here. This here is my resultant vector, is the hypotenuse of that triangle. And you go, well, how do I solve for the resultant or the magnitude of that? Well, with a right triangle, you can go back to the Pythagorean theorem, which you again should all know, but it's a squared plus b squared equals c squared. And you can say that 10 squared plus 20 squared is c squared, and c equals, should come out to 22.36 kilometers. And it looks like that.